presentation is on state of the art regarding heat and fire resistance of pultruded FRP structural members in the AEC industry, and this will be presented by Capra Williams. She is a graduate student from University of Notre Dame. Capra is heavily engaged in both research and her pursuit of a master's degree in structural engineering at the University of Notre Dame, and she intends to pursue a PhD in 2024. During her first year in South Bend, she secured an internship position at Frost Engineering and Consulting, where she aided in the design of FRP framing projects. Beyond her design role, Capra is passionate about her research, which centers on the critical areas of elevated temperatures and fire performance of pultruded FRP. I'll hand it over to Capra.
So, not only did we want to explore fire in this, which this proposal was originally on, but we wanted to also include elevated temperature because as you can see, there's several framing projects that I had the privilege to participate in as an intern at Frost this summer while also conducting graduate research. And quite obviously, they do need to meet fire standards for different building codes. And a couple of examples also are located in Santa Clara and Arizona, where you do get to start having these knockdown factors for strength in terms of the elevated temperatures that these places experience. So in order to start justifying this research, I took a look at the current status of building codes and standards, which centered around the IBC, and a few of the ones that I took a closer look at was the Oregon, Chicago, Arizona, with special emphasis in Arizona because that's where a bunch of the heavier temperature loading is taking place. And also California, with wildfires being such an obvious issue that these framing solutions would have to incorporate. And in addition, during my time as an intern at Frost this summer, we did get quite a relevant question around fire standards that hadn't quite been incorporated into pultruded FRP material data at the moment in the way that would cause it to be compliant. Let's see. So the state of where pretty much all of these building codes are now is in Chapter 6, where FRP is mentioned in one section specifically for architectural applications, and there's also a section on plastic composites, which doesn't specifically mention FRP, but it does mention wood-based plastic wood composites that seem to be pretty similar. And the big part of this is they're not structural applications of FRP that are listed in these code sections. And as I mentioned before, the Oregon regulator had a question regarding the combustibility requirements, which are required per code in the Type 2B construction that this project fell under. And as a result of the ASTM E136 not being in the material data, we had to use a different flammability standard to let them know that it was uncombustible. This type of building, the Type 2B, is a part of the subsection of the building code that lists types 1 through 5, and that goes from the most fire resistance to the least fire resistance, and there's also different subcategories, A and B, some of these building types that are fire protected and fire not protected. As I mentioned before, with the problem in Arizona is you start to experience quite significant knockdown factors in the transit temperature range from 90 degrees Fahrenheit to about 140, and then this is listed in the pre-standard, which then has temperatures above 140. You have to do additional testing in order to be able to have it pass this as a structure. And so the comparison I did was the 140 degrees across the board for polyester was about a 50% reduction in strength, and the vinyl ester ended up being around 58% as an adjustment factor, and comparatively, steel is at no reduction. Here's kind of a side-by-side of where we're at in terms of manufacturing for pultruded shades. These are flammability standards that are listed currently, and this is what the code requires. There is quite a bit of data on ASTM E84 in both. However, as I previously mentioned in ASTM E136 and UL ASTM 2652, that's not incorporated into any of the material data at the moment. And as previously mentioned by a few other presenters, ASTM E119 is not part of any data that pultruded shapes have taken place in at the moment. This also was important to consider the wood code, which the fire design is heavily incorporated into ASTM E119, and this is where I would probably see pultruded FRP shapes going in the future as well. And after that justification, taking a look at what codes currently existed, I then went through published data at the moment for FRP shapes that exists. And there was a wide variety of things that popped out at me. However, these are the ones that seemed the most applicable, and that incorporated the glass and decomposition temperature range, the different manufacturing options that this material can have, which include the resin type, the cross-section, as well as flame retardants and additives. And then, additionally, I found a really interesting paper on the residual strength properties of pultruded FRP as well that seemed very relevant. And so, the glass transition temperature, as presented by a few others, is the state at which the polymeric matrix starts to soften in the resin, and you start to see quite significant strength reduction. The interesting part about this range is that there is a high residual strength. So when you bring the temperature loading down to ambient temperature, you retain a lot of strength, which becomes important when you do consider those framing options in places like Arizona, where you end up unloading them during the nighttime. There's different temperature variations throughout the day. And the portion that was very relevant to fire was the decomposition range, where volatiles from the polymeric matrix start to be released, and the bond in between the fiber and the resin is pretty much completely gone, and there's no material strength properties, as well as the resin starts to oxidize and fibers are exposed. The second manufacturing option the first manufacturing option that I looked at was the resin. Commonly in the pultruded industry at the moment, there's polyester and vinyl ester. The polyester has high flammability and smoke production, which becomes a problem when you're integrating them into those framing options. And vinyl ester is an increased flammability resistance and corrosion resistance option. However, on the flip side, that ends up being about twice the cost, which we found out on some of the projects this summer as well. And also has a higher corrosion resistance, and the problem is also the material availability at the moment. The most important consideration I found when looking at different resins is obviously FRP has been utilized across aerospace and marine applications as well, wherein aerospace you're going to have extremely high temperature loading for multiple resins, so it is an option to switch out the resin for a higher flammability option, higher flammability resistance option. However, as you can see in the bottom, civil engineering is at a higher heat release, whereas marine and aerospace drop those down, so you do have a higher temperature resistance. However, the bulk price goes up exponentially, and with the scale of civil engineering, that isn't really a viable option cost-wise for many of these projects. So when considering the cross-section as the second manufacturing option, I found multiple papers on different values for strength, which included the compression, tensile, flexure, and shear that kind of went together. This is a normalized compressive strength data that I pulled together, which ended up showing that there's about a 70% reduction in strength at about 100 degrees Celsius. There was also flammability standards that flammability testing standards that I compiled as well, being mainly the cone calorimeter and ASTM E84. However, there was not many data points after that with other flammability tests due to them being very expensive and not a consistent testing basis for that went across papers. And so the flame retardants was actually probably the most interesting portion of this, whereas there's a variety of options for integration into the polymeric matrix with different additives, the most popular being ATH in recent years, where it acts through an endothermic mechanism where when it starts to decompose, there's water that's released, which ends up decreasing the heat that's taking place when it's exposed to fire, as well as the different smoke production by diluting the different volatiles as well. And there's also phosphorus and halogens, which act through the vapor phase of the flame. So they have an extra spot for a valence electron that ends up picking up the free radicals that are generated during the flame process. And so one of the most important testing standards that went through was the cone calorimeter test, which I accumulated the most data from. The one benefit of this is cost-wise, it's very effective to test out different resin formulations, and also a high volume of tests that has a high versatility in the amount of fires and different heat loading scenarios that you can incorporate. As you can see, small class A fires can be modeled by about 25 kilowatt per meter squared heat fluxes, and it goes from everywhere to oil fires, which ends up being about 100 kilowatt per meter squared as well. The testing outputs is also a consideration for this. So you get multiple testing outputs, which includes ignition time to smoke development and mass loss rate. So traditionally there's not that many outputs from these types of tests. And this also is able to be a smaller, more compact test that can scale to larger fire applications. This is an example of one of the data sets that I was able to find. This mainly is different ATH loadings, so it captures the different response of various resin systems, and in a cost-effective way. And the last portion of different manufacturing options that different considerations for the aggregated data set that I found was the different conditioning times. This study was a test on the residual strength of FRP, and they chose conditioning times of the 15, 30, and 45 minutes to expose these different box sections to, and they found a pretty tight grouping in between all of them. And also they did different sizes across different box sections, so you found a pretty consistent and very tight curve in between cross-section performance and also the different exposure times. Currently, what I'm doing right now is elevated temperature testing at Notre Dame, so this is the lab work portion of my research, which through the fabrication process, we got to cut up the joints, use the water jet to then create the ASTM standard dog bones. And the testing program includes 126 different tests, 7 different testing conditions, the W8 and I12 section sizes, which wasn't very common across the board. Typically, the data set had smaller section sizes than what was tested here, and also 90 and 0 degree pultruded angles. So the reason we decided to do additional tensile testing is, number one, the pultruded angles. My predecessor at Notre Dame in this area, part of his research was testing the different strength of pultruded angles in joints, and also we wanted to explore that with elevated temperatures and fire because the joints are the most critical areas of these structures, and there is an expected significant difference in strength there as well. ASTM D638 is also very common with manufacturing processes at the moment. I found a wide range of standards that were tested under these elevated temperatures because the standards haven't quite been produced for elevated temperatures in a way that was consistent across the board for pultruded FRP shapes. And this is also at a smaller temperature range, and a temperature range that's more focused on the operating temperatures that like Arizona and California experience, whereas the other studies that I found were at the higher temperature range where you would see values of 400, 600 degrees Celsius, which are very important to also explore, but there wasn't much in this range to begin with. Here's a little bit about the test setup, which we are conditioning these specimens in an oven for 15 minutes and 45 minutes. This is the location of where all the thermocouples are. Currently we have 3 on the front, 3 on the back, and picture number 3 is the heat gun setup. So when we're testing, we want to keep the specimen at the same temperature that it was when it came out of the oven. And there's also insulation that's wrapped around that traditionally, but picture that for better clarity. Some of the preliminary results that we found are for the W8 web with a 0 degree pultruded angle. There's both 15 minutes and 45 minutes in this data set at the moment. Each of those data points has 3 test specimens incorporated with it. And so the trend is pretty much what I was expecting, and they're tightly grouped and excited to pretty soon here analyze the rest of them. And that's it. If you have any questions, I'd be happy to answer them.